Yeah.
Thank you.
So I can actually hold off on the overview of what I've done so far because it's actually part of the second half of the presentation.
Oh, perfect.
Um,
Okay.
I'll do that,
Awesome.
and then I'll give a general overview of how I think some of the experience I've gained could be relevant to anybody in any field who's studying a slippery rock.
Cool.
But so yeah, so as Dr. Snow said, I'm currently at the University of Helsinki. I'm doing my PhD here, and right now I focus on clouds and aerosols and how they're related and how they affect the climate. So this is going to be a very general overview. I'm going to try to just explain to you what an aerosol is and how it's important and why you should care. So if there's any point you have a question, feel free to interrupt me. I'd like to keep this informal so we can have more of a conversation. Because if I get too technical and there's something you don't understand, I'd be happy to explain it so that you get more out of it in the long run. Um, so yeah, like I said, we'll talk about aerosols and I'll explain to you what an aerosol is. I know I'm probably talking to a lot of geologists and maybe not a lot of atmospheric scientists at all. So I'll just go very general about what an aerosol is and talk about why we should care about aerosols and why it affects everybody on the planet. And then, as I mentioned, I'll briefly discuss my career and how I ended up in this position, and I'll make it relevant for you as a student at Slippery Rock. So first, what is an aerosol? Just very generally, we can define an aerosol as a solid or liquid particle suspended in a gas. So in an atmospheric aerosol, the gas is the atmosphere. So these are small particles that are just present everywhere. And I'm going to call them particles, right? So it's common in the lingo to say an atmospheric aerosol or an atmospheric particle. So I will refer to both during this talk. So if I say particle, I'm referring to atmospheric aerosols. And they are present everywhere in the lower atmosphere. So all across the planet, everywhere. You can't really escape them. And they're very small, so they're typically microscopic, and you can't actually see them with the naked eye. And before I go any further, most people know this to be an aerosol. This is an aerosol can, and what's inside of it is an aerosol. This is not what I'm talking about. I'm talking about particles that are present all around the atmosphere, and they're breathing in right now. Right, so the first thing I'll talk about is the size of the aerosol. So you really have to understand the size of the aerosol to understand its behavior in the atmosphere. So we measure the size according to the diameter, and we assume that a particle is just a sphere. So if you imagine a small sphere, you can picture the diameter of that. That's how we measure the size. And these sizes can range a whole spectrum in the atmosphere, and they can go from nanometers to micrometers, right? So what does that mean? A nanometer is quite small. That means 10 to the minus 9, or means that there's 1 billion of them in a meter. That's also kind of hard to comprehend. So I like to think about it as in 1 millimeter. Everyone can kind of picture a millimeter as a very, very small unit. There's 1 million nanometers in 1 millimeter. So for a micrometer, that's 10 to the minus 6. There means that there's 1 million of them in a meter, and there's 1,000 in 1 millimeter. That kind of puts it in perspective a little bit. And like I mentioned before, the size has a really, really impactful influence on its behavior in the atmosphere. It defines the kind of processes that it takes part in and how it interacts with different chemicals and molecules and such. So just to give you more of a visual on particle size, because it's kind of abstract. It's not something you're used to thinking in those terms or those sizes. So this right here, this is what we call a size distribution. This is just a very general term. And I want you to notice this scale down here. This is diameter, and this is logarithmic. So this changes as a factor of 10. So this is the whole range of particles in the atmosphere. And the smallest particles we can measure are about 3 nanometers in diameter. And that's really hard to measure that. Like, what does 3 nanometers really mean? So if you picture a water molecule, right, we're talking really, really small, just a molecule. 3 nanometers is 10 times the length of that molecule. So these smallest particles are really just bigger than molecules. And then in this larger size range, it's actually a little bit easier to visualize. So this is 1 micron up to 10 microns. So this figure kind of sums it up really nicely. These are particles greater than 1 micron. The human hair is about 50 microns, or there's about 10 PM10 molecules, or a molecule that is of the size of 10 microns, can go, or sorry, 5 can go across the length of 1 human hair. And then among one of those particles, you can have 4 of these 2.5 micron particles. So that's a little bit easier to understand, but it's still very, very small, and you cannot see these particles. So now I've told you that we have these particles, and I told you that they're really small, but how many are them? So we have to quantify them using a concentration. So this is typically done in two different ways, and the first of which is called the number concentration. So this is just how many particles there are in a fixed volume of air. And we do this by quantifying the number in a cubic centimeter, right? So 1 cubic centimeter, a centimeter is about the width of your finger. So if you imagine a cube about that size, this is just how many particles fit in that little box. And then the second way we do this is by quantifying the mass of particles in a fixed volume of air. And this is typically done by quantifying the micrograms of all those particles in one volume of air, or typically in 1 cubic meter. So again, the reason we have these two distinctions is because if you go back to this size distribution, I'm going to refer to this several times, by the way, just because it's a really, really nice way to understand how particles interact in the atmosphere. So if you look at the smallest sizes, they dominate particle numbers. So it's really hard to weigh them according to mass because they're so small. And then these larger sizes dominate the particle mass. So typically when you characterize the mass, you're looking at these bigger sizes. And this is common for these definitions in research applications when you're looking at very, very small particles and physical applications. And then this is more common in air quality applications and research in that type of field. Is there any questions so far on this? No? Okay, great. So
Matt, I do have a question. Why do they clump up in different groups like that?
Oh, yeah, so that's a good question. So a lot of it comes up with their source mechanism. So there are different sources for different sizes. So like the largest particles, they have a very short atmospheric lifetime. So they're usually kicked up in the atmosphere by mechanical processes. So you have like desert dust or some kind of industry like agriculture and like wind can kick up these particles, but they're quite big, so they settle out. And you don't have a lot of growth from this size to that size because of that. And then we have a lot of particles being formed in these smaller sizes, and they can grow, and they form these distributions. So this is just kind of like an idealized distribution. This isn't what they typically look like, but you do have them forming in these modes, and it is continuous like this generally. It's a good question. So just another way to put concentration in perspective and to dig a little bit more into it is that the concentration is not the same all the time. It varies in time and it varies in space. So that's a really important concept to know because you have to make measurements all the time in order to understand how it's changing and in different locations to see how it behaves, how particles are in different locations. So under normal conditions, you have around 500 to 10,000 particles per cubic centimeter. So 500 particles per cubic centimeter is relatively clean, and 10,000 particles per cubic centimeter is what we would say is polluted. But you can actually have outside of this range, you can go down to almost 0 particles per cubic centimeter, and you can have up to 30,000, 40,000 particles per cubic centimeter in very polluted conditions. So just to put it really into perspective, imagine you have a box that's 1 cubic centimeter in volume, and inside this box you have 3,000 particles. And this is not by any means polluted, so this could be considered a background concentration of particles. And now imagine your lungs. So probably the average volume of the lungs of the people I'm speaking to is about 4 liters. And that's, I would say that's an average capacity of your lungs. So if you imagine if you exhaled all of the air in your lungs and you took a deep breath in and you completely filled your lungs with this volume of air that has 3,000 particles per cubic centimeter, you would have 12 million particles in your lungs. So there are a ton of atmospheric aerosols, and they're everywhere, and you're breathing them in right now. And there's really a lot of them. It's hard to imagine the scale of aerosols. So now, if you talk about the composition of the aerosols, you have to look at the sources, right? So this is basically the third property that I want to dig into today. So what's really important here, I mean, there's a lot of information on this graph, and this is a really nice summary of this. But what I want you to get from this is that you have different sources of aerosols in the atmosphere, and the source and the chemistry of the aerosols are directly related, which makes sense. Where the particle comes from, it's going to be made of different things. And there's 2 different types of particle sources. You have anthropogenic or human-induced sources, and you also have natural sources. These are ones that just occur in the natural atmosphere due to different processes. And it's really interesting because humans are actually changing the natural background of aerosols, which is a part of the talk that I'll get into a little bit later. But any kind of industry you have, so anytime you burn something, so any type of combustion, if you burn fossil fuels in your car, if you burn fire in your stove, if you burn anything, any type of combustion will lead to particles being produced. So just really what I wanted to get you away from, want you to take away from this is that there are natural and anthropogenic sources. This is important. And then the composition depends on the source. And then there's a variety of different sources. You don't have to memorize anything about any of these specific sources or any of the chemical composition to understand the rest of this talk. So then there's another source that I really want to speak about, because this is my research, and this is something that I really enjoy thinking about. And this is called new particle formation. And this is the process where you actually have gases in the atmosphere contributing to particles. Well, how does that work? So imagine if you have a gas molecule that's moving around, and this could be a gas molecule that has been emitted by humans, for example. So like take a sulfate molecule that's moving around, and these gas molecules are all, they're moving like this, and they hit each other and they can stick. And when these molecules hit each other and they stick, then they're moving around, and another molecule can hit them and they can stick. So they keep sticking different gas molecules to them. So you're starting from a very, very small molecule, which, like I said, aerosols are typically the smallest sizes, or just slightly larger than these gas molecules. So once you have a cluster of these molecules together, they can actually form a solid particle. So you actually have gas directly converting to aerosol particles. It's a really interesting process, and it's really interesting in the atmosphere, because once these particles form, these gases can continue to hit these clusters and these aerosols and continue to make them grow. So then you actually have a growth of these newly formed particles.
Matt, is it an actual change in the gas formation, or is it just becoming a particle because of size?
It's becoming a particle because of size. So at some point, there's not a clear distinction between gas phase and solid phase here, but they do grow to sizes where, I mean, it is at that point it's a solid particle, but they're still so small that they do behave similarly to gases, where they're moving around and they diffuse in similar ways. But because they grow to bigger sizes, they have some very important distinctions as well that make them not a gas anymore. So just to summarize this, because I know this is getting a little bit into the weeds, but you have gas molecules that can hit each other and they stick and they form these small clusters. And then if the conditions are favorable, so if you have enough of these gases present, they will continue to hit and they will stick and they will grow. And when they grow to larger sizes, they actually can stabilize and become aerosols. And this produces a lot of small particles in the atmosphere. These are very, very small particles, and they can be really high in number during a production event, which is really, really interesting. And because this is, sorry.
I was just going to say, can you just mention a little bit of, just going back to the lungs, how the particle size, the difference in particle size impacts the breathing of those particles?
I'm getting there too.
You are? Okay. Because I was just thinking, Dr. Schiappa posted about COVID and wearing masks, and I was like, oh, yeah. Okay. Sorry.
Yeah, no problem. You're anticipating a lot of my future discussion points. So, right. So now just going back to new particle formation, just because this is something I'm passionate about, I just want to give you an example and real data, which shows that these particles are forming and they actually continue to grow. So this is a plot here, and what you're looking at, this is time. Can you see my mouse here? Okay, yeah. So this is time, and this is one day on the 3rd of June. And this is particle diameter in logarithmic space here. This is in nanometers. So this is 10 nanometers and 100 nanometers. And this color is the concentration. So the red color means you have a higher concentration. So if you're looking right around this point in time, we have a higher concentration of particles in this size range. So right around 50 to 100 nanometers. And there's not a lot of small particles at all. And then as you proceed forward in time, you can see that we have a lot of these smaller particles coming into the picture. And then you can see that they're kind of growing in size. So if you actually were to track how it's growing in time, you can see this kind of trajectory. So this is actually a new particle formation event. So there's a gas phase precursor or gas phase species that is clustering, and forming new particles, and then you can actually see them growing in time as if you track this concentration. So this is a really interesting event in the atmosphere, and I'll get into why in a little bit. Right, so just to conclude, so the general points that you could take away from this, if you've never heard about an aerosol before, this is what you should know now. They're everywhere, and there are a lot of them. And they vary a lot in the atmosphere. So there's a lot of different sizes. The concentration can go basically to 0 or up to 30,000. And there's a lot of different compositions depending on where they come from. And then their properties are really important in determining how they behave in the atmosphere and how they influence other processes, which I will get into. So now I'm going to talk about why you should care about them. Now you can say something about them. Why is this relevant for you? Why is it relevant for anyone on planet Earth? Well, one of the key points that Dr. Snow already alluded to is public health. So when you breathe in the air, as I mentioned before, you're breathing in these particles. And I mentioned there's a variety of different sizes of these particles, and the size determines how far that particle can actually penetrate into your body. So you can imagine the larger particles, when you breathe in that air, they can get stuck in your mouth and your lungs. And then the smaller particles can actually penetrate further into your lungs. So when we're talking about the really smallest sizes, they can go directly into the structures inside your lungs and then be delivered directly to your bloodstream. So this is an interesting topic right now, and it's being researched because we don't know. So people put a lot of effort on the larger sizes, which get stuck in your lungs and can cause issues like asthma and such. But the smaller particles and how they're delivered to your bloodstream directly, people don't really know the epidemiology of that yet. So it's kind of an interesting research question right now. So just to summarize, the smallest particles can be delivered directly to your bloodstream. So whatever's in them is getting into your blood, which then goes to your brain or anywhere else in your body. And because of this, the current recommendations is that the lower the concentration, the better. So you don't want to be breathing in more particles. If you can be breathing in less, it's typically better for you. And I really like this photo because now this has a different meaning than it would have back in 2014. And yeah, it's really great. So this is China in 2014, and people there have been wearing masks for a very long time because particulate pollution there, particularly the larger particle sizes, what is defined as PM 2.5, you might have heard, or PM 10. These are particles in the size range of 2.5 microns up to 10 microns. And for these particles, wearing a mask is very effective. It can filter out these particles so you don't actually breathe them in. So this has been a common practice in China for a long time. And now we're all wearing masks. And I'm sure you might have heard even recently that not all masks are equal at filtering out different bacteria or viruses. And now the recommendation is even to wear 2 masks because it has a better filtration capacity. That's because these viruses that they're talking about now are quite small and can actually penetrate through. So if you just have a piece of t-shirt over your mouth, particles can go right through that, but not all the larger particles, but the really small ones can. So that's why this is a very interesting figure today, right? So air pollution kills a lot of people. People don't really realize it. It's actually one of the leading causes of death in the world, annually across the world. It kills 7 million people a year. These are 7 million premature deaths, so people that didn't have to die at that time. And this is a breakdown of the different types of illnesses or diseases that are actually caused by air pollution. And there's a lot of respiratory diseases like pneumonia and lung cancer and such, but also there's a lot of heart diseases. And this is because you're breathing in these particles that are being delivered directly to your bloodstream, which can cause changes in the physiology or the working of these organs and cause you to have some problems. And you might not think that 7 million is a lot of people, but really it is. I mean, so the population of the greater area of Pittsburgh is 2.5 million. So this is imagine about over 2 times that, almost 3 times that number of people dying every year just because of the air they're breathing. And this isn't just a problem in China or in India or places where there's high population density. This is everywhere. And 91% of the world population lives in places that exceed global air quality limits, or I'm sorry, safe air quality limits. So this is a global problem. And it's also a problem because air pollution doesn't stay within borders or boundaries. So the pollution that's being emitted in China is going to travel across the ocean and come to the US. The air pollution in the US is going to leave and go to Europe. So this is a global problem and one that has to be tackled by everyone working together. And then this is just another summary of this to put it more in perspective. So this is another report of the global causes of death annually. And you can see obviously high blood pressure due to obesity is quite high on the list, but you can look right here, you have ambient particulate matter and then household air pollution, which is also mostly particulate in nature. And just want to point out that these two factors combined are comparable to the deaths caused by smoking. So what's interesting about this is that you can choose to smoke, but you can't choose the air you breathe. So it's a very, very interesting problem that doesn't get a lot of attention, but it's a global health concern for everyone. All right, now so the second reason why you should care about aerosols are clouds. Maybe you don't know this, maybe you do, but clouds are liquid water that is condensed in the atmosphere from water vapor. And under the way that our atmosphere is right now, there are thermodynamic limitations, or water cannot condense onto itself. It's just physically impossible due to the conditions of our atmosphere. So you actually have to have something that helps the clouds form. And if I'm sure you could guess that it's an aerosol. So these aerosols act as a surface which the water condenses onto, and then it keeps condensing onto these aerosol surfaces, and then it forms a cloud droplet. These cloud droplets grow. And as you know, clouds are an important part of the water cycle. So this affects all of us. And we refer to these aerosols that act as cloud droplets as cloud condensation nuclei, or CCN. I will use that term from here on out. And it's important to note that not all aerosols act as cloud condensation nuclei equally. So this is a really interesting topic of research. Going back to the size distribution again, the size of aerosols that are typically forming cloud condensation nuclei are in this range. So 50 to 100 nanometers. So we're talking very, very small particles still. And then when they form cloud droplets, these cloud droplets grow to very large sizes. And these are typically 20 microns in diameter. So larger than particles typically are in the atmosphere. So it's quite a significant change once water condenses onto the particles in size. Right. So now, just because this is actively what I research, and I think it's a really interesting topic, is new particle formation and CCN are related. And this is because new particle formation, or whenever you have these small particles forming from gas phases, and then these particles grow to larger sizes, this process is contributing what's estimated to 50% of the CCN population in the atmosphere. So yeah, that process I mentioned earlier, it's just these gases that humans are emitting or trees are emitting, they're actually producing clouds, which is really, really cool. And this is particularly important in certain environments. And this is also my research, so I wanted to mention it so you're aware of it. The Arctic and the Antarctic are very, very unique places on the planet. And they have different aerosol properties there and different kind of mechanisms happening. And new particle formation can be particularly relevant for cloud formation in those locations, which I think is super interesting. And another reason why I wanted to bring this up is because cloud formation is not any different than new particle formation. It's actually one process. It's just happening at a different time in the process. So you have these gas molecules moving around, they hit each other and they stick, and then more gas molecules hit those and they continue to grow. So then you have particles of bigger sizes, and eventually they're large enough that then you can have water condensing onto them. And then water condenses on them and they grow. So it continues to be a growth process. It's just you have something different material or different vapor condensing onto the aerosols. So I think that's an interesting way to tie it together. Is that clear to everyone? Okay, great. So this is really relevant because clouds and aerosols are both relevant for climate in a pretty significant way. So aerosols themselves, even though they're quite small, when you have a lot of them in the atmosphere in different layers, they interfere with light. And you've seen this. So if you look up at the sky and you can see clouds and you can see the beams of the sunlight coming through the clouds, those are called crepuscular rays. the reason you can see those beams of light is because something is present that's scattering them. This is also why you have haze in cities. So there are times when the visibility becomes bad. That's because you have something in the atmosphere that's actually scattering that light. It can be ozone, or it can also be aerosol particles. So when you have incoming solar radiation from space coming into Earth, is there a question?
Well, there's two questions in the chat. Do you want me
Oh,
to?
I'm sorry, I can't see the chat. So yeah, I'd be
No,
happy to
that's
answer.
okay.
Be happy to answer those.
Actually, there's three. So one is from Samantha, and it says, "Is there less?" Wait. So is there less of this particulate pollution in the United States and other countries, since masks are really only worn in the Asian countries?
Yeah. So the answer is yes. Yes and no. So there is more widespread particulate pollution in certain countries, China being one of them, because they have a lot of people living in these city centers. But there's also quite bad air pollution in city centers in the US too. There have been more stringent restrictions put in place. I mean, there's the Clean Air Act that has been put into place, which has actually done a lot to clean up the air in the US, which is a really great thing. We became aware of this back in the 70s, and a lot of work has been done since then to improve the air quality. So yes, it's true, but there are also localized places where you can have just as bad of air pollution. And I mean, I just read an article just today or the other day that New York City subways are supposed to have really, really, really bad air quality. That they were like, wow, people should have been wearing masks here for a long time because it's actually really, really bad. So yes and no. Localized, it's the same, but in general, yeah. Currently, it's less in the U.S. There's a less population density, so that's part of it.
Okay. The next question was, can we ingest these aerosols through our water sources?
Yeah. Yes. Yes. So rain out and the formation of clouds is actually an important clean out process for these aerosols, right? So you can imagine when you have droplets that fall and these aerosols are in the air, they can actually scavenge them out. So rain and fog formation and things like that actually does clean out the atmosphere a bit, and then that's going to go into the waterway. Now, the concentration of these particles compared to anything else that's already in the water is going to be quite low. And I mean, the size of the actual mass that's from the aerosol that dissolves and is inside the water is quite low. So yeah, in a way, you are breathing them in. A lot of the smaller particles that do act as cloud condensation nuclei are nothing that's you should really be concerned about. A lot of it does come from like just organic vapors that come from trees. But yeah, some of these compounds are ending up in the waterways.
And Matt, in follow up to that, once the condensation commences and proceeds on the condensation nucleus, is it not the case that the water can dissolve the original solid substrate and they become aqueous ions? So we're drinking that in the chemistry, but not as a solid particle that might play, for example, havoc on your stomach lining.
That's absolutely correct. And I guess that's kind of what I was implying, but without saying it as poignantly as you just did. So yeah, and one of the key factors contributing to an aerosol's ability to act as a CCN is solubility. So Dr. Burkhart's absolutely right. So as these cloud droplets form, the actual aerosol seed particle is typically dissolved. So yeah, you're breathing in the chemicals, but not necessarily aerosols themselves. Now that's not true. There are insoluble particles, and this is a study in water quality, such as turbidity, and the actual sediment in the water. But that's something different. Great. There was another question too.
Yeah. With more air pollution, are there more aerosols, and is there more cloud formation because of it?
That is a great question, and that is exactly what I'm about to get to. So I can answer the first part of that now. And yes, when there is more air pollution, there are more aerosols. So like I mentioned before, there are natural sources of aerosols, but there's also anthropogenic aerosols or human created aerosols. And when we are producing pollution, we are emitting more of these aerosols. So yeah, that's why in larger cities, you have a larger concentration of aerosols. And so I'm going to get into the cloud part of it very, very soon. Okay, so coming back to climate and incoming solar radiation. So as I mentioned, you have a column of aerosols and you have incoming solar radiation. And these particles can actually interfere with this incoming solar radiation and they can actually reflect it back out to space. So that means that less of this radiation actually reaches the surface. And radiation is just a fancy way for saying temperature. So this actually really affects the energy balance at the surface and the temperature. So aerosols can actually contribute to cooling in this way. And then now clouds are a key part of this too, because clouds are also reflective. You can see clouds, they're white. So that means that they scatter, they're scattering light in some way. And this is another way that aerosols contribute to climate. And it's the same as aerosols before. Clouds actually can reflect away some of this incoming solar radiation back out to space. And clouds are more efficient at scattering than aerosols because they're larger in size. So I showed that there's quite a difference between the size of a cloud droplet compared to an aerosol or the newly formed aerosols. So this is quite a significant enhancement in their scattering ability. So just getting into the polluted versus unpolluted. And this is where humans come into the mix, right? Because there were clouds present before there were humans because of there are aerosol sources, but humans are now adding to that. And also in general, just if the concentration of natural aerosol sources change, this will also be reflected in that. So imagine an unpolluted cloud and a polluted cloud, and the amount of water in the atmosphere, assume it's the same, so the amount of water in the cloud is exactly the same. But if you have a polluted cloud, you have more particles what the water can condense onto. The particles are smaller. The cloud droplets become smaller, not the particles. The cloud droplets are then smaller. So this water is distributed into more particles. So this is important because then seems like you're artificially increasing the number of cloud droplets by adding more particles. So this has two important behaviors in the cloud that actually influence its radiative abilities. So like I mentioned, if you have constant water content and you increase the CCN concentration, you increase the reflectivity of that cloud. It has a stronger albedo, as we say. So that cloud is actually more efficient at scattering light because it has more of a more scattering inside the cloud due to more of these cloud droplets at just slightly smaller sizes. And then you increase the lifetime of the cloud. It's because clouds form rain, and rain droplets are very, very large droplets that fall from the cloud. If you have smaller droplets inside the cloud, they're less likely to grow to sizes where they will fall as rain. And both of these effects result in cooling at the surface. So if you have two clouds and one is more polluted, the more polluted cloud will have a stronger cooling effect on the surface. And in relatively clean conditions, this is actually very significant. So trying to understand this and how we are influencing things over the background concentration in a lot of places is a pretty significant research question that's ongoing right now. I hope that answers your question now about the pollution in the clouds. So don't take my word for it. You can actually look at this yourself. This is a visual depiction from satellite images from NASA. So like I said, there's the direct effect where aerosols scatter particles, or sorry, the aerosol particles scatter light themselves, and the indirect effect. You can see this is looks like a dust storm coming from Africa. So desert dust is a very common natural aerosol source from these dust storms, and you can see over the ocean, you can see the particles are actually scattering light back out to space. That's why we can see them. And then here, this is also over the ocean. This is these are ship tracks, and you can see the ship tracks that are actually putting out pollution are brighter, and you can clearly see them over the rest of the clouds, and that makes them more reflective to incoming solar radiation. So that's why we can see them as being brighter in these images. Right, so this kind of ties all of the climate system together in terms of what we understand with respect to human-induced climate change. So at the very top of this, this is what we know about the greenhouse gases. So the amount of uncertainty, or these black bars here, is quite small when it comes to greenhouse gases, and the level of confidence is quite high in our current understanding of these contributors to climate change. Now, if you look at aerosols, which are right here in this center section, the uncertainty bars are enormous. And actually, these two error bars here, and there are some processes in here that I did not go into detail in this talk, but these two error bars contribute the most significantly to this source of the total aerosol, I'm sorry, the total greenhouse gas irradiated forcing by humans. So this is the biggest challenge right now to being able to model the climate and to being able to understand and predict how things could change in the future as we continue to emit greenhouse gases and as we continue to change the land surface and such. So I hope that's clear to you now.
So,
yeah.
So what basically what you're saying is when we're trying to predict things related to climate change in the future, we don't know the behavior of these aerosols in terms of the climate system, and so there's this huge uncertainty. Is that?
Yeah, so there's a huge uncertainty. We know which way they tip the scales, but
Okay.
but because
So they're cooling.
yes,
Okay.
there are circumstances where they can induce warming effects as well, but I don't want to get into that now. I don't want to confuse you. But in general, clouds lead to cooling, and yes, they're contributing to uncertainty. So to understand these processes in the context of everything else in the atmosphere, we have to understand them at a process level. And because there's such a variety of aerosol in the atmosphere and variety of compositions and sources, and the concentration changes in different locations, it's really, really hard to track down exactly how this is happening. So I mentioned my research is new particle formation in CCN. That's what I'm most interested in. So how do these gas phase precursors that are present all around the world contribute to particles in certain environments? And it's not easy to do. It's actually very challenging to measure. You have to have some very sophisticated gas phase mass spectrometry equipment, which is not easy to operate in the field. And putting it all together is where this large uncertainty comes from. It's a very challenging process to pick apart and understand and put it together, and especially to model it in a climate model.
Yeah. So Elena has a question, and she says, do you think that the increase in cloud reflection is part of the Earth system's way of basically fighting back against the climate change?
That's a fantastic question, and that's one that has been asked before. That's actually there's a hypothesis put out about this that phytoplankton, once you have more CO2, the phytoplankton become more active and they emit more particles because they actually can emit gases that can then be transformed to particles or to form new particles. And people were thinking that is this their way of responding to it? And it's the same type of thing. I don't think anyone knows the answer for that. I don't know if it's a symptom or if it's a cause, but it is something that is happening. I don't know if the Earth has. I don't know. I think it's more physical. It's just a physical way of the physics of light and everything like that. But it is certainly a feedback loop. So there are a lot of feedback loops built into the climate system, and that's whenever one thing happens and it starts to push in a certain direction, you can have things that push it back, or you can have things that go uncontrolled and they actually increase because there's feedback loops. So kind of ties into that. Great. So this is a topic I want to introduce just to kind of, I really like it because it's something that's going to be, I think, becoming more prevalent in the future. And I think that you should be aware about it in the context of aerosols and clouds and climate. And I think it's also a really nice way to tie together everything I just told you about aerosols and clouds and climate. So this is gaining popularity in research and also in governments. So I want you to be aware about it. It's how can we take advantage of these properties for our advantage, right? So if we can increase the concentration of aerosols in certain clouds, we can make them have a stronger cooling effect. So can we do this to offset changes that might be concerning due to greenhouse gas warming? Because if you want to develop your country or your nation, you have to burn fossil fuels and greenhouse gases, right? There's a lot of nations that want to become more developed, and to do that, currently have to burn greenhouse gases. So in order to allow everybody to do this, they're saying, well, what if we just put a whole bunch of particles in the atmosphere, and we can, create more clouds, and we can cool the planet, right? So it seems like a feasible thing, but it has some interesting considerations, as you might already understand now based on what I've told you. So this is literally just producing clouds artificially. And as I mentioned, there's a lot of moral and ethical debates about this, and people are starting to discuss this, not just on a small scale, not just for research, but national governments are actually starting to discuss this as something we can do to mitigate possible changes in the atmosphere due to too much warming. And I hope this causes you some concern. So whenever you hear this again in the future, which I expect this will become more popular in the news or such as we continue to progress, but I just want you to keep in mind that clouds really are a key part of the water cycle. And if you could control where clouds are forming and how clouds are forming, you can control where it rains. And if you control where it rains, you control a lot more. And that's really a scary thing. And that really should scare you. If it stopped raining in the places where you produce your food, you don't have food production anymore. And I really hope that is clear. And I just want to remind that everything in the environment is actually connected. So if we're going to change the water cycle or change the clouds and such, it could lead to unforeseen circumstances that we don't know yet. So, there's certain plants or animals living in a certain region that has a certain climatology, and if we change that climatology very, very quickly by artificially changing a process in the atmosphere, then it's going to have negative impacts on that organism, and that'll affect everything else in the system. So just want you to keep that in mind when you hear this in the future. So I just want to conclude this topic. So why we care about aerosols. As I mentioned, they're critical in cloud formation, and without aerosols, you don't have clouds. So this is really interesting too. In the Arctic, sometimes the concentration is so low that you don't have any aerosols, which means you have no CCN. So when this happens, you can actually exhale, and it's cold outside. And usually when you exhale and it's cold, you can see your breath. But you can actually exhale in the Arctic sometimes and not see your breath because there's no particles for the water vapor to condense onto. So without aerosols, there are no clouds. It's a very, very important relationship. And when you perturb this aerosol cloud interaction system in the atmosphere, we have changes to the radiative balance. And these changes are currently the largest source of uncertainty in our climate system. This is the big question right now that we're trying to track down in order to understand how climate can change in the future with less uncertainty. And like I mentioned previously too, particulate pollution is also a significant global health problem, and it doesn't get a lot of attention, which is, I think, really surprising, but it does affect everyone on the planet. Right, so now I want to shift gears a little bit, and I'll briefly go, I know I'm running out of time, but I'll briefly just go into my career development and how I ended up here. And I want to put this in context with you, the students at Slippery Rock, because I started Slippery Rock and I have some experience from being there. And I want to say, what can you learn from my experience that's relevant for you and for your career development? So this is the path. I started at Slippery Rock, and I did my bachelor's degree in environmental science, which I imagine most of you are also doing. And then I got a position as an air quality research technician in Bermuda. And then from there, I went on and did my master's at Dalhousie University in Canada in physics and atmospheric science. And then I got a job as an instrument technician in Palmer Station in Antarctica over winter. And then I got a job working at Brookhaven National Laboratory, which is part of the Department of Energy in the US. And I was an aerosol measurement engineer there. And then I quit that job to go work on an expedition in the Arctic for about 6 months It was called the Mosaic Expedition. It's actually the largest expedition to have ever taken place in the Arctic, and it just recently ended. So I'll just briefly describe each of these situations and what I learned and how it's useful for you. So when I started Slippery Rock, I didn't know what I wanted to do. I was a pre-pharmacy major, and maybe I'm talking to some, younger students who don't really know what they want to do. I think it's okay. I started as a pre-pharmacy major, and then I switched to Parks and Recreation during my first year. I had no idea what I was doing. I was just trying new things. I had no idea. And then it was the end of my second year, so almost halfway through my undergraduate career, that I finally found environmental science and stuck with it. I took some courses that were, I think they were great. I took physical geology with Dr. Schiappa. I took environmental problems with Dr. Snow. I took environmental geology with Dr. Burkhardt. And after taking those classes, I was like, I need to switch to this major. And then I took a lot of other courses, which were really great. So it's okay to not know what you want to do right away. I didn't have it figured out. Most of you might not have it figured out. Some of you might be ready to graduate and have it figured out. That's great, but not everyone does. So it's okay to try new things and change your major if it's not working for you. And then I would say, just in general, just try something new all the time. Just keep trying new things, because you might find something that actually is really nice, try a new elective in a different major. You might enjoy it. And even if you don't, if you find yourself doing something that you don't like, you've still learned something, which is that you don't like it. And that's equally as important, especially earlier in your career. That's right. So just then later, the very second half of my career at Slippery Rock, I was taking all these geology courses in environmental science, and it was really cool. I really liked it, but I never saw myself becoming a geologist. And I was like, well, this is concerning. I mean, I found something I like, but I don't really see how I fit yet. And then I didn't really know that I wanted to do atmospheric sciences until like the end of my third year. So, almost a year into graduating, I still didn't really know what I want to do. I took air pollution meteorology, and I was like, okay, this is what I want to do now. And then after I knew that, I was talking to Dr. Snow, and there was a position that opened up at the Slippery Rock University Air Quality Observatory, which, if you don't know about, ask Dr. Snow. I'm sure she'd be happy to tell you about it. I went there and I collected air samples. It wasn't a difficult position, but it was some experience, and that experience paid off significantly. So try to learn as much as you can. You never know it'll be useful. The world is becoming more and more interdisciplinary, so it's useful to know as much as you can in the field or in different fields, because it all applies. And in the environment, particularly, everything is connected. So this gives you different perspectives as you approach the problems that you might face in your career or in your research, depending on what you choose to do. And then I would say gain as much experience as you can in the professional world as soon as possible. So I would say the most important thing I've done at Slippery Rock was collecting air samples every 6 days at the Air Quality Observatory, because that has propelled me further. Obviously knowing everything in your courses is really, really great, and you really should do that, but having professional experience is what's going to get you a job and what's going to move your career forward. So you have to do both. So this is important too. So you just engage with the professional community. You're going to learn about yourself, what you like, what you don't like, what you're comfortable with, what you're not comfortable with, who you want to work with, type of work you want to do. Do this as soon as you can. And if you don't know how to do this, I recommend Googling research experience for undergraduates, or REUs. I really wish I would have known about this, because there are people right now who have money who want to pay you to work with them for a summer to do research projects. And they're all over the world, and all you have to do is apply. Doesn't matter what your major is, you sent an application and they will take you. In Bermuda, they did this where I worked, and there were students who would come and they would live on the beach and research marine biology. Google it. I highly recommend it. There's people everywhere in the world doing this right now who will pay undergraduates to do research. So this is my first job. I worked right here. It was really quite nice. And, I wouldn't have gotten this job if it wasn't for the work I did at the air quality station, because I was basically measuring air quality in Bermuda. This was a great job. I started learning networking skills and communication skills. It was great. But I wouldn't have gotten this job without that position. That's the main takeaway here. And it's really, really important to gain some exposure to the professional world now, be that an internship or anything, as much as you can. Just gain some experience that's going to help you be more competitive when you go into the job market. Doesn't matter what your field is. Right. And then I went to Canada and did my master's degree after working there for a bit. And my technical experience in Bermuda is what got me here. So it's a stepping stone. One thing leads to another. And I was researching aerosols, as I'm sure you probably know. And yeah, this is another key point here. So there was something that came up that was not directly related to my research, but it was they had their boat that they wanted fixed. And they're like, hey, we want to fix this boat because it does oceanographic sampling. And it was kind of related to my research, but not really. And they're like, do you know anyone who has any technical skills that could try it? And I was like, I'll give it a go. Why not? I'll do it. Why not me? And I would say that it's probably actually been the most influential thing that I did during my graduate degree. And it wasn't related to my research because they sent me to the Arctic to deploy this boat. And here's me in the Arctic deploying it. It was an oceanographic sampler. I won't get into it, but I helped rebuild this thing and I went to the Arctic because of it. It was not related to my research at all. So any kind of extra opportunity you have earlier in your career, take it because you don't know where it's going to lead you. And it'll increase your network and it'll open doors for you. So I then went to the Antarctic, and I can tell you with certainty that I would not have gone here if I didn't have the technical experience building a boat that I did, and then also working in the Arctic. So I would not have gotten to do this really awesome thing that I've always wanted to do if it wasn't for that. And I was helping biologists do fish research. So it wasn't like I was doing anything that was completely related to my career, but I tried something new and I loved it. It was great. So I just mentioned that already. Yeah, so this has been incredibly valuable to me. It wasn't related to my research, but it got me somewhere else and got me new experience. So having a variety of different types of experience is actually quite valuable. And once you've done a winter in Antarctica, people are very interested to hear about it, and then it helps you get jobs too, because you can sell it in a variety of different ways. So this is exactly what happened here. I was working with the Department of Energy, and I almost out of time, but I was working with the Department of Energy here, and I was looking at aerosol instrumentation. We'd make measurements around the world. So I was traveling all the time, Argentina, Norway, all over the place. So we would just make these measurements, and that's what I was doing there with them. And I would not have gotten this job if I didn't do the work I did in the Arctic and the Antarctic. They were looking for someone who could work in the field and was comfortable fixing things. And both of those jobs gave me the skills I needed. And literally every single thing that I have learned in my career at this point was useful in this career or in this job. And this was my dream job. So really invest what you can and try things because you don't know how it'll pay off, and the skills you're building will help you. But then I quit this job to take part in this campaign I was talking about that happened in the Arctic, where they parked the boat in the Arctic and they let it drift for an entire year making measurements. It's the very, very complicated logistically and also very complicated and interesting scientifically. So I was there for about half the campaign, and I had to quit my dream job to go do this. So, but it's worked out for me because right now I'm in a different position, in a different place, and I'm doing things that I enjoy. And I would not be doing that if I did not seize this opportunity. So you have to take risks and sometimes seize these opportunities. And then just some general advice is I never felt in my personal career like I was ready to take the next step ever. You know, I'm like, well, what if I'm not going to be able to do this? I'm not going to be able to do that. But you just have to do it. It's like you just take the plunge and you learn how to swim. That happens all the time, every new position, every new job. So apply that. And especially if you're going into a scientific career or if you want to be anything related to the environmental field, I suggest you learn how to program. Just learn how to load a data file, perform some simple calculations, and make plots. It'll do a lot for you. And Python is free. You can download it and take free courses right now. I recommend it. And then you have to apply yourself. So you can't get where you want to go if you don't apply yourself. You have to work hard. And there's no shortcut to get somewhere that's worth going. Right. So with that, I'm all finished. It's a little long, I guess, but happy to answer any more questions you might have.
That's awesome. By the way, I think it was New York Times just had a huge piece on Mosaic. So I don't know if you've seen that yet.
Yeah, there's a lot. There's actually a few documentaries coming out about it too.
Oh, cool.
Yeah, if you're interested, I can pass you along a link. So
Absolutely.
Yeah, it's really, really cool. I recommend Googling the Mosaic campaign and checking into what's been happening there. It's really, really an interesting look at the Arctic. So
yeah, polar bears.
Yeah, polar bears and yeah.
They had a picture of polar bears like climbing up a flag, like trying to
Yeah,
You guys had flags on the ice, and there were
yeah,
two polar bears out there. Oh my
yeah.
God.
Yeah, I was there. I was there when that happened. That was pretty.
Yeah.
It's pretty cool. So when you get to go and you see these things in real life, it's so much better than you can even imagine. It's just it's magical. So I recommend you apply yourself and you study and you get the experience you can to try to do these types of things. There's people out
Does
there willing to pay you to do it. that's
yeah,
that's the
yeah.
main thing. Yeah. So
Does anyone have any questions? I saw Lang had one about is it different to apply to grad school in Canada than in the US?
yes and no. The big difference was that I did not have to take the GREs in Canada. So it's actually one less step and a little bit less money, but otherwise it was quite similar. And I would say that the academic system in Canada and the US is a lot more similar than it is now. Like in Finland and Europe, it's a little bit different than it is in the US too. So if that's a consideration for you moving forward.
Does anyone? Yeah. This was great. Some people have to leave. Good luck to you.
Oh,
Any
thank you everyone for listening.
Does
Matt,
anyone else have questions? Yeah. Okay.
so I just want to say, Matt, that you exemplify that you can make your own luck. I really strongly believe this. When you put yourself in good places in the company of good people, the cards fall, and one good thing often leads to another. And you just did a beautiful job of showing that you can make your own luck. And also, I want to let you know that recently I listened to a book on tape. I mean, I read a couple books too, but I like to take in more literature than I can actually read. So I also do books on tape. And I just listened to an absolutely outstanding science journalism piece called The Alchemy of Air. The Alchemy of Air. And I recommend that to you, Matt, because
Yes,
you're going to dig it. It's going to blow you away.
thank you.
You bet.
I will certainly check that out. Yeah, I love that stuff.
So, I don't see any questions in the chat, but this was super interesting and inspiring. Thanks so much. I really enjoyed your presentation. Helpful advice. Does anyone else have any questions? No? Okay. Matt, thank you so much. That was fantastic.